Yes, so good evening. I hope I am audible. So my name is Aditya Sharma, and this is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into the last week of this course. So this was a 12-week course, and we are into the last week of this course. So theme of today's discussion is blade design, cascade theory, and turbine cooling method. So related to the contents of this week's uh, related to the content of this week, we will be having a discussion on this and few questions based on that we shall see. Very basic questions. As per the questions that have been provided in the assignments. So, instructor for the course is Professor Vinayak Kulkarni from Department of Mechanical Engineering again, and I'm a research scholar here, serving as a teaching assistant for this particular course, and also taking these tutorial sessions. So I'll wait for another 5 minutes to see if somebody joins, and after that we can start today's session. Thank you. Okay, so we can start today's session, but before starting today's session, in the chat, I have one query regarding assignment number 9. Okay, so this is from, yes, from SGG. Hello, sir. So maybe just give me a second. Uh, Allow my camera, yes. So, I have solution for this question. So here you are writing that in the solution T naught 3 minus T naught 1 is taken, and T naught 3 is not taken. This is what you are saying, that isentropic total temperature has been taken, and this
No, no.
yes,
Correct, correct.
yes,
But I feel it
isentrop
should be the actual.
it is so I have in this tutorial session, I have, I believe, done this question. So there, isentropic we have calculated. First, T naught 3 dash we have calculated from the this pressure ratio. So pressure ratio we had.
Okay.
So from there we can calculate the isentropic.
Okay.
Yes, and
Okay.
then we have this efficiency of the compressor we have.
Correct, sir.
So compressor's efficiency is T naught 3 minus T naught 1 divided by T naught 3 minus T naught 1.
Correct, sir.
So from here, if we place T naught 3 in the left hand side and all other terms in the right hand side, from there T naught 1 is given to us. Yes, T naught 1 is given to us. T naught 3 dash we just calculated from RP, from the pressure ratio.
Okay. Okay.
And further this T naught 3 we can calculate, and here I can see that Cp delta T, for Cp delta T, T naught 3 minus T naught 1 we have taken, not T naught 3 dash.
But in the calculation, it is T naught 3 is used, not T naught 3 dash.
Yes, the actual one we are taking.
No, but in the calculation, actual one is not used. In the
Okay,
calculation,
okay,
which are
okay. So a solution has been provided, you are saying.
solution has been provided, but in that solution, TO3 dash is used.
Okay, okay. So there,
Isentropic TO3 has been used, not
there
actual
can.
TO3.
Okay, okay. So what happens is, so this TAs. So the week 9 to 12.
Fine, fine. That is fine. You
Yes,
just
yes,
explain
yes.
me what should be used. I have no
T naught,
problem.
T naught
Just
3 is T naught 3 should be used.
actual one.
Yes, 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 yes.
Okay. Okay. Thank you.
Yes,
That is what I
yes,
wanted to know.
yes, 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 yes.
Thanks a lot.
I'll also communicate this to the TA who is taking care of this, because
Correct, correct.
yeah, because it will
Okay,
fetch
sir.
marks. Yes, thank you.
Yeah,
Thanks
yeah,
a lot. Yeah, thanks a lot.
yeah, yeah.
So in that case, because the doubt uh, we could discuss, so we will continue with today's session. So this is blade design, cascade theory, and turbine cooling method, right? So
Yeah.
yes. So maybe if you would not mind, you can mute yourself, and if you have some doubt, then you can ask uh, if that works for you. All right. So the contents of today's session are as follows. So four lectures basically were there. Actually, five lectures were there, but then the last lecture is numericals. So that I'll not be discussing. Then lecture number 38 is cascade theory and blade design. Right. So introduction, sorry, of this has been done. So what is a cascade and what is cascade theory, and how we use it to design the blades and turbo machinery. Okay, so I'll briefly discuss the topics and then we shall see few questions related to that, right? Then we'll move on to lecture number 39, where the variables based on which we discuss the cascade theory has been discussed. And then uh, two two topics are there. One is your turbine cascade, and then is your compressor cascade. Okay, so we shall see this. And here the diagrams are important. So it's important that I have been repeating it again and again that it's very important that we are able to visualize. Okay, the blading we are able to visualize. If we are able to visualize the blading, then it becomes very easy for us to understand all this. So if we are not able to visualize it, then it's very difficult. Then questions related to it. Okay, then lecture 40 is again on velocity diagrams of turbine cascade, and then same for compressor cascade. We will discussing the the topics. So topics for turbine cascade and compressor cascade are same, but it's just that uh, in the turbine cascade we'll be discussing the blading for turbines, and in the compressor cascade we'll be discussing the blading for compressors. So then we'll see. So because I don't have questions for compressor cascade based on the assignments we have. Okay, then we'll move on to turbine cooling methods, and then we shall see two questions on this turbine cooling methods. Correct. So so lecture number 38. Then we have the topics. The major topics are first, the cascade has been introduced, and then one-dimensional flow and what are its limitations. This has been discussed. So topics I'll discuss briefly, right? And then cascade performance. So first is your cascade. So what is a cascade? If you see cascade. So what we are doing, because if you see in your turbo machinery, so we have one shaft, right? And then we have blades connected to this shaft or hub, if you say. So I'm saying shaft, you can uh, take it as hub. So, right. So there are blades connected to this. So till now the discussion had been about one blade and then the velocity diagrams related. But then in actual, you have a cascade, right? A number of blades you have. So when we are trying to study the behavior of flow that is passing through these blades, the more realistic approach would be to study this flow is in the cascade form, right? So that is basically the whole idea behind this cascade theory, right? Then, so there are two types of cascades. One is your rectilinear cascade. Okay. Then is your annular cascade. So what is rectilinear cascade? So rectilinear cascade or straight cascade basically is you are arranging blades in a straight line. Right? You are arranging, so you have one blade here, one blade here, one blade here, one blade here, one blade here. So this is basically your rectilinear cascading. And what is annular cascading? Annular cascading basically is, so you have blades on the hub. So this basically is this. Yes, if there is some doubt. Okay. Then this topic is one-dimensional flow. So this I have discussed that. Just give me a second. Yes, so I have discussed that. Till now, the discussion we had is considering that this is one dimensional. There is no dimensionality in it. So we are not considering the arrangements, the number of blades that are there and how flow moves in between these blades. So we are not considering that, right? So what are the limitations of such discussion? So the limitation is, first of all, there is three dimensionality to it. So there will be vortices, there will be in the flow, right? So if we are just considering a streamline and one dimensional flow, in that case, we'll not be able to have a comprehensive view of the flow in your, which is passing through these blades, right? So in that case, this is a major limitation, right? Then is arrangement. So how the blades are arranged. So how one blade is arranged with respect to the second blade. So this also will have effect on the. So this we also need to consider. Right? So this basically is has been discussed in your one-dimensional flow. Then third is your cascade tunnel. Right? So So I'll just draw a schematic here. Right? So you have a blower, the components. So basically, this is a wind tunnel type of arrangement. So as I've said, that cascade basically is a type of wind tunnel type of arrangement. Right? In wind tunnel, what we do, we study the aerodynamics. Right? The flow is moving there, and then some aerodynamic body we keep in the test section, and then we uh, study its aerodynamics. Right? So here, the cascade tunnel will have a blower, right? And then there will be a conical diffuser, right? To slow down the speed of this flow that is coming. Then this flow that is coming will settle in settling chamber. Then honeycomb structure will straighten the flow, right? And then there is contraction section, right, to speed up the flow. And then you have this test section, right, in which you will keep your cascade. So, but then what is cascade? We have discussed, right? So cascade is a number of blades arranged. So it can be a rectilinear cascade, it can be an annular cascade, right? So in the lectures, so starting from lecture number 38 to lecture number 40. So the cascades that have been drawn are rectilinear cascades, right? The straight cascades. So So one diagram I will draw just. So how the arrangement there is in the test section of your cascade. So this I'll just draw. Right. So yes. So C1, CX1, fine. Yes. So what I have drawn basically is the test section region where your cascade has been placed. Now we want to study the flow. So, so you have this initially you have this velocity c1, okay, but before this, so this has been drawn, so you should be able to visualize this, right? So this basically is the top section, top view. So if blade is like this, okay, so this is the cross section of the blade. The topmost section is the cross section of the blade. So this has been shown to us. So these one, two, three blades have been shown to us. So this basically is a cascade of blades, one, two, three, so which is placed in your test section. So flow is moving like this, and you have blades like this, one, two, three, four, in this. Okay. Then the C1 is the initial absolute velocity that you have. So this has been divided into two components, x and y. Right? And then at the end again, you have C2 absolute velocity, which is divided into two directions. One is x and one is y. With respect to this plate, right? With respect to these plates. So x and y has been decided with respect to these plates. Okay. Then, then is your cascade performance, right? So in cascade performance, what one important thing we consider or we take care that we should not have pressure losses. In the flow studies, this has been our concern, right? Pressure has always been our concern. So we want to reduce always this pressure loss. So while we are considering this flow analysis, so we want the pressure loss to be minimal. So these are the topics that have been discussed and in detail. So these have been discussed in your lecture number 38. Then we'll move on to few questions based on these this lecture number 38. Right? It's a very basic question. So I believe you can answer this very easily. So let's just do this. So, first question says that in a cascade, when a row of blades are arranged in a straight manner, it is called as a rectilinear cascade, this annular cascade, or a straight cascade, or both the options are correct. So these questions are from one of the previous assignments, right? So we have just discussed it that this is a rectilinear cascade, we call it, right? And then we call it straight cascade also. So in that case, the option comes out to be the correct option. So after that, we have next question. So let's see the next question. So please read this and try to answer. So this question says that in the flow analysis of a cascade, two-dimensional assumptions are suitable for dash. So two-dimensional assumptions are suitable for what type of blades? So this is what the question says. The four options are there. First is high hub to tip ratio blades, low pitch to EH chord ratio blades, high pitch to chord ratio blades, and low hub to tip ratio blades. So chord, what is a chord? What is pitch? Okay, so this has been discussed in lecture number 39. Okay. So maybe I can discuss it first and then we can take this question. This comes in airfoil nomenclature, which is lecture number 39. So I'll but discuss this here only. Airfoil nomenclature. Lecture is from lecture number 39. Okay. Topics related to lecture number 10. We'll take. So So in the airfoil nomenclature, so the line joining your leading edge, okay. So the leading edge of your aerofoil. So the cross section of your blade that we have been drawing is called an aerofoil. Okay. So you see this figure, the leftmost point in this blade is leading edge, and the rightmost point in this blade is the trailing edge. Okay. Then this is the T max is the maximum thickness of this blade. So this is basically about your foot. So first is high hub to tip ratio blades, low pitch to chord ratio blades. Pitch basically is the distance between two blades. In a cascade, distance between two blades is your pitch. So this is denoted by S. So high pitch to chord ratio blades, low hub to tip ratio blades. So this has been discussed, okay, that two-dimensional assumptions are suitable for high hub to tip ratio. So A is the correct answer to this question. Then this question is there. It says that in a cascade tunnel, in which of the following sections the velocity of the flow remains constant? Four options happen to you. One is your settling chamber, one is your honeycomb chamber, one is your test section, and fourth is that all the options are correct. So for this question, option D will be correct. So in all these sections, we want that our flow velocity remains constant. Okay. So D is the correct answer to this question. Then yaw meters are used to measure the four options are there. So this has been discussed in lecture number 38. So yaw meters are used to measure the absolute magnitude of flow velocity, correct direction of flow velocity, pressure over the cascade, or pressure inside the test section. In the wind tunnel, so this has been discussed. So when we want pressure profile, what we do, we have ports. So I am drawing circles here. Okay. But in reality, this will be like this. You have ports like these. On the surface of the airfoil. Okay, then you have two tubes from here. You have tubes from here passing. So for all the ports, so somewhere you'll have its exit of these tubes. So wherever you are measuring the pressure, be it your manometer or some other pressure transducer, whatever it is. So this way you do basically. All right. So these ports are basically on the surface. So this has been this was drawn in the lecture, so I'm just elaborating a bit more. So yaw meters are used to measure uh, the correct direction of the flow velocity. So this is what we were discussing. Question on yaw meters. So correct answer to this question is option number B. So this is used to find the flow direction. Okay, so I have in advance revealed the answer to this question, but then we'll discuss this also. Just give me a second. So this is the question that we are discussing. This is in a cascade tunnel, which of the following sections are responsible for reducing the turbulence present in the flow? So answer to this question is honeycomb. It's honeycomb chamber. Honeycomb chamber used to reduce the turbulence in your cascade tunnel. The right answer to this question. Then lecture number 39 is there. So it has topics, cascade variables, aerofoil nomenclature, turbine cascade. So this we have already discussed. Now I'll discuss cascade variables and turbine cascade. In the turbine cascade, we'll be here getting introduced to various angles that are here involved in the analysis of the cascade. Okay. So cascade variables, first of all. The different cascade variables. One is your Reynolds number. Which is rho CL by mu. Rho is density. Rho is for density, C is for velocity of the flow. Okay. L is the length scale. In case of our blades, it will be the chord of the aerofoil of the cross section of the blades. And then in the denominator, you have viscosity. Then is Mach number. Mach number is C by A. Where C is the velocity of the flow, A is the speed of sound, the medium, or in the flow, in the fluid, the flow of which we are studying. Now here you have pitch to chord ratio. So this is S by L. S is pitch. Then is aspect ratio, which is H by L. So I hope you understand this. So this is your blade. This is its height, and this is its chord. And this is the aspect ratio. Then blade symmetry is there. Then boundary layer. And turbulence. Then incidence angle. The angle which with the flow is interacting with the blade. So these are the variables involved in a analysis of a cascade. Then airfoil nomenclature we have discussed. Then I have not discussed one thing here, that is camber. Right. So this I had drawn. And what is camber? Camber basically is if we have an airfoil, let's say this is airfoil. So how do we know what is camber? Camber basically is, so along the x-axis if you move, okay, along the x-axis if we move, so one is this point and this point. Let's say we are at this x point. So the mid of this upper one and lower one. Okay, width of this. Then let's say we move at this point x2. Let's say this is x1 to x2. Then we have this line at x2, then upper one and lower one. Then let's say we have x3, this should be 2, 2, and 3, lower 3. So the center of U1 and L1, center of U2 and L2, center of U3 and L3. So this way, all the points, if you consider on the x axis up to your length of chord length. So you'll have one dotted line. Okay. In case of a symmetric airfoil, this camber line, this dotted line will be on the x-axis. But if the airfoil is not symmetric, for example, let's see, this is the shape of airfoil. Okay. In that case, if you want to have this dotted line, that what I'm saying. So let's say at this x point, now you see L is U is this and L is this. So dotted point will be somewhere here. This will be something like this. It will be. So this basically is your camber line. Okay. This dotted line we call as camber line. This something. Which has also been drawn. This basically has been drawn. There is some airfoil whose camber line is like this. I have drawn one camber line here, right, along with the airfoil, but then just camber line has been drawn, and then this has been shown that this is your leading edge. This is your trailing edge. This is your maximum camber by non-dimensional lengths along the x and y axis. So this is what a camber basically is in an aerofoil. So before moving on to the turbine cascade, we will take a short 5 minutes break because it's already more than 1 hour since we have started this session. So we will take a short 5 minutes break. After that, we will continue the session. Thank you. Okay, so turbine cascade. So angles, we'll see different angles. Three angles are there. One is your camber angles, then uh, camber angles and blade angles, then air angle. So if this is the camber. Okay, so first I was showing airfoil like this. Now I've kept it like this. The airfoil is shown. Then this is leading edge. This is trailing edge. This is I1. This is T2. This is theta. So what this is? This is timberline. This is leading edge. This is trailing edge. So when we draw tangents at the leading edge and at the trailing edge, so these two tangents meet at one point and the angle they make, okay, with each other is this theta, which is called blade camber angle. And theta is blade camber angle. I want I three R what camber angles. One second, if we see let's draw this. This is your chord line. This is your tangents to the chamber. Yeah. Then we have angles defined. So we draw the angles first. This is stagger angle gamma. This is alpha 1 dash, which is blade angle. This is so this basically is angle between chord line and tangent to chamber line. But because here your vertical line, the axial direction line, and the chord line and same, so there might be confusion. The confusion can arise from here that it is with the vertical line of the axial direction line and nothing like that, but it is the chord line and the tangent to the chamber line. So which is clear here in this diagram. Okay. This is your chord line. Right, two. Now if you have this vertical line drawn here, with vertical line and this. Chord line, you have stagger angle again. And this whole angle, right? Vertical. Is blade angle. Is stagger angle between chord line and z direction. Then and for the shot, lead angles. So now blade angles we have seen, stagger angle we have seen, blade camber angle we have seen, camber angles we have seen. Then we are left with air angles. So this I have here. What I'll do is I'll just draw flow. This is C1. Let's say it is moving out this direction C2. Then this angle is alpha 1. This angle is alpha 2. Just give me a second. Okay, so this is your air angles. Okay. Alpha 1 and alpha 2. So I hope this is clear. This is basically axial direction. This is the axial direction. This is Let's see information. Thought this is tangent to angle. This is what we were, right? So this is your blade angles. This is your chamber angles. This is your chamber angles. This is your blade angles. And this is your air angles. So these are the angles of concern in a turbine cascade. Then there are few other angles which are derivatives of these angles only. One is your incidence angle I, which is alpha 1 minus alpha 1 dash. Then is deviation angle del, which is alpha 2 dash minus alpha 2. Then is your deflection angle, epsilon, which is alpha 1 plus alpha. So these are different angles that have been discussed in lecture number 39 related to turbine cascade. So camber angles are there, then blade angles are there, alpha 1 dash and alpha 2 dash, and then air angles are there, alpha 1 and alpha 2. Okay. So this is about lecture number 39, and then there are questions related to it. So three topics, then questions, let's see. So this here says that for the flow expression of cascade aspect ratio, choose the correct option for alphabet A. A by L we have been given. So out of the four options, aspect ratio, now if you see in the cascade variables, aspect ratio is H by L. H is height of the blade. So the correct option out of these four is option number 8. The next question is for a turbine cascade, a camber angle is defined as camber angle is the angle between camber line and initial direction of flow, two tangents to camber line, angle between chord line and lines tangent to camber line tangent to camber line. So camber angle is the option if you see. Let's see the angles drawn here. Camber angles these are here. So this is between chord line and tangent to camber line. So C is the correct answer to this question. Then next is for a turbine cascade and deflection angle is defined as the dash. So what is deflection angle? So let's see. We have discussed deflection angle. The deflection angle is this. This is alpha 1 plus alpha 2. What is alpha? Alpha is here you see alpha is the air angles. Okay. So out of these four options, if you see difference between the camber angle at the inlet and blade angle at the outlet, summation of air angle at the inlet and the outlet, difference of air angle at the inlet and the outlet. And fourth is difference between the camber angle at the outlet and blade angle at the outlet. Camber angle, blade angle. This is alpha 1, alpha 2. This is alpha 1, this is alpha 2, this is alpha 2. Fourth is camber angle from the outlet. Which is alpha 2 minus blade angle is alpha 2 dash. So this is the correct answer for this question. Then moving on to next question. Okay. So rather than question, we have now topics of lecture number 40 and lecture number 41. Then we have two questions. After that, we will conclude the questions. So in turbine cascade, we have seen different angles. Then here velocity triangles have been discussed. Then continuity, mass conservation equation, momentum equation in y direction, momentum equation in x direction. Then lift and drag have been discussed. So I'll draw the velocity triangles here. I believe that will suffice and that will do the job of understanding all other related topics. Then compressor cascade, I will skip because just blading is different. Otherwise, uh, it is a lot of similarities are there in these two topics. So I'll just draw the velocity triangles for turbine cascade, and then we'll move on to lecture number 40. So lecture number 40, turbine cascade velocity triangles we are discussing. Forty. Velocity. This is lift, this is drag. This is the resultant force. So these are the velocity triangles involved in a turbine cascade. So if you see the first velocity triangle, C1 is the absolute velocity, and then in the X and Y directions, uh, this has been components have been given. Then you see this at the exit, you again have C2 velocity. Okay. Then there is axial direction, and then this is Y2, Y direction. Then alpha 1 and alpha 2 again are blade angles. Okay. Then there is mean mean position also, where you have mean velocity, and this mean velocity has been divided into X and Y components. Then there is this force. Force is there in X and Y directions. But then this force has X in X and Y direction, you have these two forces, which eventually is this resultant FR force. Okay. But this also is force, FR force also is the combination of lift and drag forces. So in terms of lift and drag, if you divide it, okay. So lift will be perpendicular to the direction of the flow. Okay. And then drag will be in the direction of the flow. Okay. These are the directions of lift and drag. So these have been shown here and here. So these are the velocities involved in the turbine cascade, which have been shown through velocity triangle. So S is the pitch. Okay. Then So then based on this only other these discussions on momentum, continuity, momentum in X and Y, lift and drag has been done. So this I'll not discuss. I'll just give the link of lecture number 40, the description. You can just go through. Same is with the compressor cascade. So from the link only, so all this can be covered. Link you can find in the description. Then is lecture number 41. So turbine cooling methods. So why do we need cooling basically? So we need cooling because we have seen in the previous weeks discussions, in some of the previous weeks discussions, that will increase in temperature, right? Increases your efficiency, also the power output. Right? So now the temperature is increasing, but will the blading and the material of the blade that we have chosen will be able to sustain this heat? Okay, so this becomes an issue. Right? And to tackle this issue of temperature, okay, the cooling is required. And for that purpose only, this turbine cooling is being discussed. So lecture number 41. So if you see, two diagrams have been drawn. This and this. RP is your pressure ratio. This is your Tmax. Okay, the temperature at which your gases enter the turbine. When one I'm discussing this turbine cooling methods, in which I have drawn first the efficiency versus pressure ratio, then I have drawn power output versus pressure ratio. So how this graph, what this graph shows us, and how the maximum temperature, if we increase, leads to increase in the power output. So this basically this graph shows. Right? So internal cooling, what happens in internal cooling? You have a blade. So from the hub, what we do, we let the air pass. Okay, you have pores or passages here. You have passages here up to tip. You have such passages through which your air passes. So this is called internal cooling. So within the blade only this air is moving. So it will be here, 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 here. So this basically is internal cooling. So internally all this happens. Then there is external cooling. So where what happens is at the surface also you have some opening. Okay. So this air that is coming from here, let's say it is coming here, so it will have went out here also. Okay. So this will create some layer between this surface. Okay. So it will pass through surface also. So this basically is external. So we have one question in it. So this is so internal and external cooling. Then you have component matching. So what happens in component matching? So this basically is in off design conditions. Okay. When we have to understand the flow, right? In off design conditions, we have to handle the flow in flow analysis in off design conditions. In that case, we do component matching. So how do we do it? We do it with the help of mass conservation, energy conservation, okay, momentum conservation. Right? So all these things are taken into consideration. Then lecture 42 is questions only. So now then coming on to questions. The first question is, in case of internal bleeding, an air blanket is formed in terms or in case of it should have been external cooling. An air blanket is formed dash for cooling between blade surface and hot gases. Inside the blade passages at the hub of the blade at the tip of the blade. So this is A option is correct. A is the correct answer to this question. In case of internal blade cooling, cooling of the blade is achieved by modes of conduction, convection, both conduction, convection, convection. So this is by conduction and convection. So C is the correct answer to this question. Best answer to this question. So this is it about today's session. We have come to the end of this session. So I'll just conclude the session. So 5 lectures were there, out of which we discussed 4 lectures. First, so this whole session was on cascade theory and turbine cooling methods. So in cascade theory, we saw what is a cascade. Okay, the arrangement of blades. So rectilinear straight cascade and then annular cascade and then we moved on to turbine cascade, right? We discussed cascade tunnel also. So we study the cascade in a cascade tunnel, right? And then we saw the turbine cascade. Okay, we saw its different angles involved in its analysis and the velocity triangles related to it. And then compressor cascade has been discussed. Right? Its velocity triangles and then its angles involved in it in its analysis, and the lift and drag forces that uh, it encounters. Okay, both both types of bleeding that they receive. Okay, because of flow, the lift and drag that they receive. So this has been discussed in lecture number 39 and 40. in lecture number 14, majorly, or specifically in lecture number 40. And then lecture number 41 was on turbine cooling, where we saw why we need turbine cooling and two methods, two broad methods. One is internal cooling and second one is external. So all these things were discussed, like, right? So this is it about today's session, session number 12, and also about this course. So this course has come to an end. Right? I hope this was a learning experience to uh, all the students, okay, who have been through this whole course. So as far as these lectures are concerned, so this is it for this aircraft propulsion course. About these live tutorial sessions, so this was week 12. Related to week 12, we had this session number 12. Then again, we have planned one more session that will be on 16th of October. That is day after tomorrow. Okay. The timing will remain same 6 to 8 p.m. So there we will be, so it will be a conclusion of this course where we'll be briefly just have the overview of different topics that we saw in each week. Okay. So everything we cannot, obviously we're not going to go, but we'll just touch upon what we learned in different weeks. So it will be a 2 hour session. So let's see. Okay. So this is it about today's session. Thank you. Thanks for watching this session.